So a common form of account that you might see is an account that's compounded. So this is where it's building on the interest that you've already earned. So with simple interest, what we saw is that it was always based on that initial deposit that you put in the account. But with this, it's going to be that if you've earned more money on that account, then when it adds percentage next time, it's taking percentage of that amount with the original amount as well as the interest that you already have. So it's a much better form of account. You'll make more money off of it than a simple interest account. So let's see how this works together. And just like that last example, I'm going to give you kind of a breakdown so you can start to see the formula working. But in terms of the first year, it's going to look pretty much the same. What we're going to do is take that $500 and add on 6% of that 500. So I'm going to take that 500 plus that 6%, which would be 530. Now, in terms of a breakdown, I'm going to use a similar form. What we ended up with simple interest, I wanted us to look at that 1 plus 0.06 and then see how that time came in as a multiplier there. I'm going to do a similar thing here, but I'm going to change this a little bit in that I'm going to simplify this to look like 500 times 1.06. What this is doing right here in notation is taking our initial amount, and this right here translates to 106% of that amount, which is exactly what we want to do adding interest on. We want to add that 6% on, but we also want to keep that initial amount. So 106% of 500 is 530. So then when we go to this next year, what we want to do is take 106% of that 530. So what I'm going to do is write this out in terms of a calculation. It's like I have my initial amount. We took 106% of that initial amount, and that got us to 530. Then what we want to do is take 106% of that calculation. So what I want to do is multiply on 1.06 again. So what this would be is 500 times 1.06 with an exponent of 2. So we'd be taking that 106% twice. Similarly, when we get to year 3, we'd start with that 500, and we'd want to take 106% of that value 3 times. And then for year 4, 4 times, and year 5, 5 times. So with this, we can plug this into the calculator, and we'll see this 561.8. So when we were doing simple interest, that year it was 560. By adding that $30 twice, we can see we make a little bit more here. And then 595.51, 631.24, and 669.11. And then with seeing this breakdown here, we can start to see how the formula comes together. We'll have our principal, so we'll have our starting amount. We'll have 1 plus the rate that we're using to represent 100% with that added on rate. And then in the exponent, we'll be seeing the number of years that have passed, because that'll bring through this idea of how many times do we want to take that 106%. So this account, it's considered compounded yearly, and we'll look at different methods of compounding. So this is specific to compounded yearly, and we'd find the amount for our account, the balance, by taking our principal times 1 plus our rate raised to an exponent of how many years have passed. So let's do an example with this. We have $200 to invest, so that would be our principal. And our bank is going to offer us 2 options. So sometimes they'll offer different percentages based on different compounding methods. So account A is going to be investing the $200. It earns 5% interest every year for 15 years. So notice the word compounded doesn't come up there. So what we're going to be using there is the simple interest formula, where the amount is coming from the principal times 1 plus the rate times time. Whereas with account B, they have this percent interest rate, and you can see it's compounded yearly. So that's where we want to use this new formula of 1 plus rate raised to the period of time. And then this will also be 15 years. So you can see and banks would do this where they would change the percentage that it's working with. Because if you just have the same percentages, then compounded will obviously be better. But what they can do is lower the percentage for when it's compounded, and then in the long run, it might be hard to see which one's an actually better account. So if we plug in our values, so with account A, we have our principal of $200, 1 plus, and then our rate is 5%. So we need to plug in 0.05, and then times time of 15. If we plug all of that in, we should be getting a balance of $350 after 15 years. Whereas with account B, we'll have our principal of 200, 1 plus the rate of 0.042, and then our exponent will be the number of years, 15, and this will be 370.72. So even though it's a lower percentage rate because it's compounded yearly, account B is better. After 15 years, you'd end up with more money in that account. So this is compounded yearly, so each year it would build on this amount that's in the account. What if we compounded more times per year? So some terminology you might see, and it's listed here on this page. We could see compounded quarterly, monthly, daily, and even continuously, which will be a bit of a special case that we'll talk about when we get there. But the idea is like compounded monthly is that at the end of each month, you have interest building in this account. Now, with these problems and with the setup down here, you can see we have our principal, and then we have this percentage rate. And what you might see for this percentage rate is terminology of APR, annual percentage rate. So what they'll do is they'll tell you a percentage rate that they're working with across the year. But if we're compounding, say, monthly, it's that it's 6% over the year. So as we're compounding, we need to divide that up into 12 pieces as we use it. So we'll have to divide this rate. And then also in terms of how often our account builds, it's like if it builds for 5 years, but if it's compounding monthly, it's like, well, in terms of how many times that account has grown, it's been 12 times per year for 5 years. So our time is going to adjust a little bit. So in terms of notation, it'll be very similar to what we see up above here, but what we're going to add on is this notation N, which is going to represent the number of times per year that the account is compounded. So when you see N, it's the number of times per year the account compounds. So in terms of form, it's going to look a lot like up above in that for the amount, we'll take our principal and then we'll have 1 plus, and then before where we had the rate, what I was saying down here was that if we're compounding multiple times per year, but this rate represents an annual percentage, we need to divide that up. So what we're going to do is take that rate divided by how many times per year are we going to compound. So if it was monthly, it'd be taking that rate and dividing it up by 12. And then in the exponent where we had time, which represented like here, it was yearly. And so overall that account would compound 15 times. Well, with these where it's multiple times per year, it's that like if it was monthly, it was that 5 times for each of the years, but then 12 times per year. So we need a multiplication of the number of years times this number of times we're compounding per year. So in our exponent, we're going to take the number of times we compound times the number of years. This formula right here is actually the same formula as here. It's just when you're compounding yearly, then n is equal to 1 because it's once per year. So by having a denominator of 1 here, it would just turn into r, and having a value of 1 there would turn the exponent to t, and it becomes that exact formula that we see up above there. All right, so with this example, let's see how this formula works. And actually with this worksheet, I'm going to draw a little line here because I want to show something off to the right when we get to the next page. So just leave a little space to the right, but on this left-hand side, I'll show you the formulas. So simple interest, that formula was our principal times 1 plus r times t. So what we'll do in this case is take 500 times 1 plus the rate of 0.06 times the 5 years. And that would be the 650 that we found. Compounding yearly, as we saw, that would be the 500, so that would be our a equals p times 1 plus the rate, and then time becomes an exponent when we're compounding. So we'll have 500, 1 plus the rate, so that 1.06, raised to 5, so that would be the 669.11. Now when we compound quarterly, we're going to take that formula, but now we'll have n. And when we're compounding quarterly, this number of times we compound per year is going to be 4. So we'll have 500 times 1 plus the rate of 0.06 divided by n with an exponent of 4 times the number of years. So let's go and see how to plug this into an online calculator, because often with financial mathematics, that can be the trickiest part. So I have my online calculator with Desmos here. If you want to use the GeoGebra one, it's a very similar setup. So what we'll have is we'll type in the principal, and then parentheses 1 plus, and then a nice function here so that you can type it like you're seeing how you've written it on the paper is if you want a fraction, there's this a divided by b portion right here. So if we click that, it'll set up a fraction for you so you don't have to worry too much about parentheses or order of operations. You can just type it in like that. So 0.06 divided by 4. And then it gives you kind of this shadow here just to show you that you haven't closed your parentheses. So we started parentheses. When you're in the denominator there, you can either click with your mouse to the right hand side, or if you click the right arrow on your keyboard, it'll bump you out of there. And then we can close our parentheses. And then we want to start an exponent. So there's this button here with a with the exponent of b. If you click that, it'll bump you up into the exponent. And then we're going to be plugging in some calculations into the exponent. And when we do this, you're going to want to have parentheses. So I'm going to go ahead and start parentheses and then write my 4 times 5. So 4 for quarterly and then 5 years. And that'll give me that 673 point. And then with these, we're going to want to round to 2 decimal places since it's all financial. So we'll have a 0.43 at the end there. So what we can do is then go back to our page, and this would be 673.43. The only thing we needed to add in as we were writing there into our online calculator was having parentheses there. If we go to compounded monthly, that's where we'll have compounding 12 times per year. So it's a similar setup, 500, 1 plus 0.06 divided by 12, and then in the exponent 12 times 5. So if we go back to our online calculator, if you already have the form there, you can just edit like you would a Word document, and that I'm gonna change that to a 12, and then 4 is gonna change to a 12 as well. And then we have our solution there, 674.43. And then for our last one, compounded daily, we'll use 365. So this is where our account would be growing every single day. So with this, we'll have our principal, we'll have our percentage rate, but it needs to be divided up across each of the days. And in terms of how many times we compound, it's 365 days per year for 5 years. And when we type that into our online calculator, you should get a 674.91. And then to go from here, it's like to compound even more, more than daily. We're going to see this case where we're compounding continuously, so the account is always growing, but we're going to look at this later. We'll need some extra notation for that case, but we'll look at that in the next video. So as you can see, comparing these accounts, like compounding is best, and the more it compounds, the better in terms of having a fixed rate and the number of times per year you compound. But what they'll often do is kind of trick you with it in terms of like compounding more per year for a lower percentage rate. So they'll kind of adjust how many times it compounds with the rate and have it work out fairly similarly. Now, for comparing accounts to see which is the better deal, which one will make you more money, a tool that we often use is the effective rate. So effective rate kind of takes away the idea of a principal for the account and just gets at what percentage growth are we having per year. So that's what effective rate does, because like this compounding daily, even though they're giving you this annual percentage rate of 6%, because you're compounding daily, you're actually getting more than 6% over the year. It's just the 6% is kind of part of this base calculation for how that account's going to work. So even though they're saying 6% across the year, when you compound more times per year, that percentage is actually a little bit more. So what we can do is find this actual percentage growth in 1 year and compare those values, and that can help see which account is going to be better. So when we're compounding, to find this value, you'll take 1 plus the rate divided by n raised to the power of n minus 1. So this takes away the variables of having a principal, because the idea of it doesn't matter how much money you input, we just want to know what's the percentage growth. And also it's this percentage growth over 1 year, so we don't need a value for t plugged in, because we're just assuming over 1 year what kind of percent growth are we seeing. So this is where I wanted this kind of extra column on this page, is that I'm going to show you the effective rate for each of these cases. Now, with these first two, it's not going to be too exciting. When we have simple interest in terms of percent growth each year, that's always 6%. Same thing with compounding yearly. Those are 6% growth. So those are just kind of given to you. But like compounding quarterly, where we're using this 6% multiple times per year, to see our actual percentage growth, what we'll do is take 1 plus the rate of 0.06 divided by 4 raised to the power of 4. And if we take 1 away, then we can see our percentage growth, which would be a 0.0614. So we're actually getting 6.14% per year from that account. For compounding monthly, similar idea of 1 plus 0.06 divided by 12 to a power of 12 minus 1. That'll give us a 0.0617. So that account is actually growing by 6.17% each year. And then compounding daily, 1 plus 0.06 divided by 365 raised to the power of 365 minus 1 for a 0.0618. So that account's really growing by 6.18% per year. And again, this continuously one we'll talk about later. So this percentage rate can give you just a clear idea of what percentage you can expect per year from that account. So let's look at some examples here. We are investing $500. We have an annual percentage rate of 4%. So here's our principal, here's our rate of 4. And it's going to be compounded monthly. So that's giving me a value for n. And we want to determine the effective rate. So what we'll do is take 1 plus that rate of 0.04 divided by 12 raised to a power of 12. And then we're going to take 1 away. And that'll give us a value of 0.0407. So this account has an effective rate of 4.07%. So even though they're giving us that annual percentage rate of 4%, really if it's compounding monthly, we'll see that account grow by 4.07%. seeing which account is a better deal. And as you can see, they're giving us very minimal information here in that there's no principal, there's no amount of time, but we don't need it for the comparison. So this has a rate of 0.061 compounded quarterly. So that'll give us n equals 4. This has an APR of 6.05%. And it's compounded daily. So this is that case where compounding daily sounds better because it's compounding more often. However, it's at a lower percentage rate. So with that, it can be hard to see which is better. So let's compare the quarterly account with the daily account. Now, with these cases of comparing effective rates, you might need to go out to a few decimal places to really see how different they are. Especially like in this case, these percentages are so close to each other, 6.1% and 6.05%. So I'm just going to grab a bunch of decimal places when I do this. So let's see, quarterly. So I'm just going to copy from the calculator 0.062, 409,615. And then for compounded daily, 0.0605 divided by 365, raised to a power of 365 minus 1, and then just copying from the calculator as much as I can. Because what you'll see is they're similar in that like 6.2%. Here we have a 4 that would round to a 4. But if we go out far enough, and even if I just change this to a percentage, 6.2409615% versus 6.2362271%, what you can see is that about here, we're seeing different digits, and this is a higher percentage. This quarterly account is better. We're going to get a higher percentage rate over the year. And yes, it'll come down to like a difference of pennies maybe over the year, but if you have this account for a long time, those pennies can turn into dollars, to hundreds of dollars. So any little difference can make a big change.